Reality, as you experience it right now, completely falls apart below about 1/10 billionth of a meter. At that scale, the rules that let you catch a ball, boil water, or orbit a star simply stop working, and a new rule book takes over. The rule book of the quantum realm. The quantum realm is not a different place in space. It is a different regime of physics, the world of the unimaginably small. Roughly speaking, it is the scale of atoms and below, from about 1/10 of a nanometer, the size of a hydrogen atom, 1/10 billionth of a meter, down to distances far smaller than a proton. At these scales, the constants that usually hide in the background of our lives, like Planck's constant, suddenly dominate. And when Planck's constant matters, intuition breaks. In everyday life, objects follow definite paths. You throw a baseball, and in principle you could track its position and velocity at every moment. That's classical physics. In the quantum realm, an electron in an atom does not have a neat little orbit like a miniature planet. Instead, it exists as a probability wave, described by the Schrödinger equation, that tells you the chances of finding it here or there when you look. Before you measure it, it is not somewhere. It is a spread-out cloud of possibilities. This is why quantum mechanics feels so alien. A single electron fired at a barrier with two slits will build up an interference pattern on the other side, the kind of pattern you get when waves overlap with bright and dark stripes. It is as if that one particle went through both slits at once, as a wave, and interfered with itself. Only when we detect it does it choose a location. In the quantum realm, particles are also waves, and waves are also particles. The strict boundary between thing and motion starts to blur. Energy, too, comes in chunks. An electron in an atom cannot have just any energy. It can only occupy discrete levels, like steps on a staircase. To move between these levels, it must absorb or emit a quantum of light, a photon, with exactly the right energy. This quantization is why atoms emit very specific colors when heated or excited, forming spectral lines. Each line is a fingerprint of allowed jumps in the quantum realm. So how is this world different from ours? In the quantum realm, you get superposition. A system can occupy multiple possible states at once, encoded in a single combined wave function. You get entanglement. Particles separated by kilometers behaving like a single unified object. Their properties correlated more strongly than any classical signal could allow. And you get inherent uncertainty. Even with perfect instruments, you cannot know both the exact position and momentum of a particle. This is not a limitation of technology, it is a feature of reality at small scales. The strange part is, this quantum realm is not somewhere else. Every atom in your body, every electron flowing in your phone, obeys these rules, all the time. The normal world is what you get when you average over countless quantum events, when decoherence and sheer numbers wash out the weirdness into the smooth, predictable behavior we call classical physics. But to really understand how the universe works, we have to go back down and ask how these bizarre microscopic rules give rise to our familiar macroscopic reality.